The simple definition of a gas is that it is a state of matter that will take the shape of its container. It will also occupy the space of the container it's given. We're going to expand on that definition of a gas, and we're going to say that the particles or atoms that make up a gas do not interact appreciably with one another. There is a lot of empty space between each of the particles or atoms that make up a gas. Now, these gas particles are in constant motion, and because they're in constant motion when they are in a container, and let's just draw them in this container here. So our gas is down here, and the gas particles are in constant motion, so they're always banging into the sides of the container. But because they do not interact appreciably, and there is a lot of empty space, they have the room, and they don't necessarily react. They simply push on the sides of the container. And that force is called pressure. We use pressure to describe our gas. So pressure is the force exerted on the sides of a container by a gas. Now, the units we use for pressure are oftentimes the atmosphere. Sometimes you may see Pascal and its related kilopascal. You may also see pounds per square inch, sometimes abbreviated PSR and the torricelli, or you may see millimeters of mercury or inches of mercury. So be sure that you remember how to convert between inches and millimeters. Now, 1 atmosphere is defined as 1,325 pascals. I don't know why they didn't make it an easier conversion, but that's what it is. 1,000 pascals is 1 kilopascal. So that means 1 atmosphere is 101.325 kilopascals. 1 atmosphere is 14.7 psi, or thereabouts. It's close enough. 1 bar is 100,000 pascals. 1 torr is, or 760 torr, I should say, is 1 atmosphere. And 1 torr is equivalent to 1 millimeter of mercury. In my classes, I have a particular affinity for the atmosphere, and PSI is something we use in the United States an awful lot, so this is a conversion you should memorize. Torr is also often used, as is the millimeter of mercury. It is possible but not probable to see inches of mercury, but as I mentioned, knowing the conversion between inches and millimeters, you should be fine with seeing in inches of mercury. Pascal and kilopascal are not as often used in my classrooms because students who typically take my class aren't going to use those particular units. Now, the higher up we go, the less air pressure we have pushing down on us. So if we were in Denver, Colorado, and it had an air pressure of 12 psi, let's convert that into atmospheres, bar, and torr. Now, we capitalize a torr because it is named after a scientist, and the convention is to give a capital letter to the units that are named after scientists. So make sure that that torr is capitalized. So if we start with our 12 psi, and I'm going to convert that into atmospheres first, remember how we use our conversion factors. So we know that 1 atmosphere is the same as 14.7 psi. This is like multiplying 12 by a fraction that's 1 because they are equivalent. My PSIs will cancel out, and I take 12 divided by 14.7, and I get a value of 0.816 atmospheres. Because I started with 2 significant digits, I need to report 2 significant digits, so I would report 0.82 atmospheres. If I'm going to convert that PSI into bar, well, if I scroll up just briefly, the conversion that I have is that a bar is that many pascals. And I have pascals to atmospheres, so I can go PSI to atmospheres, then atmospheres to pascals, and then pascals to bar. Don't be intimidated by using several conversion factors. As long as your units cancel out, you should be fine. So first I convert my PSI to atmosphere. Then I'm going to take my 1 atmosphere is equivalent to 101,325 pascals, but the question asked for bar. So now I'm going to take 100,000 pascals and convert that into 1 bar. So when I perform that arithmetic, and what that means is I'm going to multiply 12 times 1 times 101,325 times 1. So that's everything in the numerator on the top of my line. And I'm going to divide it by the product of what's on the bottom, 14.7 times 1 times 100,000. And I get 0.827 bar. Now, because I only started with my 2 significant digits in my measured quantity, I can only report 2 significant digits, so I would report 0.83 bar. Notice how bars and atmospheres are very similar, but they are definitely different. So now I'm going to convert this into torr. This time I'm going to take my 12 psi, and I will start by converting it to atmospheres, just like I did above. Now I'm going to take the relationship that there are 760 torr in 1 atmosphere. So what I get is 620.4 torr. Because I have 2 significant digits, I have to have 2 significant digits here. So you can either report this as 6.2 times 10 squared torr, or you could use the more ambiguous 620 like this. Just do not put a decimal there. That makes the 0 significant. So 620 torr. Now, I mentioned the torr was named for a scientist named Evangelista Torricelli, and she was an Italian physicist and mathematician, and she discovered and designed the barometer. The barometer is used to measure our air pressure. Now, the manometer is a similar device that's used to measure blood pressure, but it's also used to simply measure the pressure of a gas in a closed system. Now, there are times, and I'm probably going to butcher this, but I'm going to try. So if we have a bulb that has a tube like this. All right, that's the best I can do. So if we put a valve here and we have a gas in this bulb, I suppose, and that gas, all right, that gas is represented by the white parts in my shape. So this part here is probably something like mercury. Now, a manometer can be open or closed. That means open to the atmosphere, where we have to take the atmospheric pressure into consideration, or it can be closed. So the gas is only pushing on the mercury itself, and it's not dealing with the atmospheric pressure pushing down. So this manometer can measure this gaseous system, the pressure of this gaseous system, and we can regulate how big of a sample we have. So if what we do is we measure the distance, the height distance between the 2 edges of our mercury. So this distance here is related to the pressure. Now, if we measure this in, say, millimeters, then what we're left with is millimeters of mercury, because this is oftentimes going to be mercury in a manometer. It could, if we have a sample and let's say this distance is 13.7 centimeters of mercury. And let's say it's open and it's at sea level, so we have our sea level pressure to contend with as well. What is the pressure? And what is the pressure first in millimeters of mercury? Well, since I'm given 13.7 centimeters of mercury, that's a pretty easy conversion to do. I know that in 1 centimeter there are 10 millimeters, so I should have 137 millimeters of mercury, but we're not done. Because I said this is open and we are at sea level we define that the pressure of the atmosphere is 1 atmosphere, or 760 millimeters of mercury. Then we have to add it together. So if you have an open manometer and you have a distance here, you need to take into consideration the pressure, the atmospheric pressure. So I would take my 137 millimeters of mercury and add it to the atmospheric pressure, which is also pushing down, to get a pressure of the gas is 897 millimeters of mercury. Now, if I'm going to convert that, say, into atmospheres, then I need to use my relationship. So I have my 897 millimeters of mercury, and I'm going to use 760 millimeters of mercury is in 1 atmosphere, and you should get about 0.18 atm atmospheres. That would be just for the distance here. So it's 1.18 atmospheres. 3 sig figs here, 3 sig figs in my original measured quantity. So just a reminder, whenever you have an open manometer, you have to take into consideration the atmospheric pressure that you're given. So now we're going to build on our definition of a gas, and we're going to use what's called the kinetic molecular theory. Now, the kinetic molecular theory has 5 precepts. The first of which is that gas is comprised of molecules in continuous motion. So continuous motion is important. Now, remember that continuous motion, that kinetic energy, tends to be proportional to temperature. So keep that in mind. Now, these gaseous molecules or particles, not only are they in continuous motion, but they travel in straight lines. They also change direction when they collide with either each other or the walls of the container. Now, the molecules of a gas are negligibly small compared to the distances between them, so they have a lot of empty space. I said that at the beginning. The pressure exerted by a gas in a container is the result of the collisions of the gas on the container. So we have that pressure definition. Gas molecules or particles have no attractive nor repulsive forces, so they are not appreciably interactive. And 5, the average kinetic energy of a gas is proportional to the Kelvin temperature of a gas. So the average motion, I'm not sure what that's supposed to be. The average motion of the particles is related to the temperature. Now, whenever we talk about gases, whenever we do calculations, we need the temperature in Kelvin. So you will always have to convert your temperature to Kelvin. You may want to review converting Fahrenheit to Celsius and then Celsius to Kelvin. Now, these postulates help to explain the behaviors of a gas that we can distill down to a few gas law equations. So we have Daltons, we have Charles, Boyles, and we have Daltons. Now, we can combine all of these and then form what's called the combined gas law, and I'm just going to touch on that briefly, but I'm not going to go into that too much. So Daltons we're actually not going to do much calculation with, but what Daltons says is that if the temperature increases, then the average speed and energy also increases. So that is, if volume is constant, then pressure is going to increase as well. We're going to show this with the combined gas law. Charles' law states, if the temperature increases and P is constant, then the volume, it will also increase. So we have a proportional relationship, and we show that with V1 over T1 equals V2 over T2. Now, I'm going to work some problem examples here in a minute, but this is the relationship you need to remember. Boyles Law states that if the volume you think about a piston, and we have this container, and it's a closed container, and we have this piston. So we have this gas at some pressure and some volume, and we drive that piston down. What we do is we're compressing the gas molecules now. So now they take up less space with the same number of molecules. So here I have 6 drawn. So now what we have is a decrease in volume but an increase in pressure, because these same 6 gas particles will be hitting the sides even more often. So that's called an inverse relationship, and we show that with P1 V1 equals P2 V2. With Avogadros Law, you can assume we're going to be talking about something having to do with moles. And what we have is basically the more gas we have, the N, the more volume we have. So we have this direct proportional relationship. So V1 over N1 is going to be equal to V2 over N2. Then we have Dalton's Law. Now, Dalton's Law is going to be the easiest of all of the gas laws, because what Dalton's Law tells us is that the pressure of a mixture is going to be the sum of the partial pressures of each component of the mixture. So that's the easiest one to work with, because as long as your pressure units are the same, you can just add them together. Now, we are going to do a little bit with the combined gas law because most books do cover it. And that's just P1 V1 over T1 equals P2 V2 over T2. So it's really a combination of Charles and Boyles. So how do we use these gas laws? We'll start with Charles' Law. Now, Charles' Law is the law that governs hot air balloons. So if we heat up the gas that's contained in a balloon, its volume will expand. So that's how hot air balloons are filled. Now, if we look smaller, and we have a sample of gas that occupies a volume of 0.033 liters, and that is at 10.0 degrees Celsius at 750 torr. What is the volume? So we know we're looking for our volume. That's going to be our variable at 30 degrees Celsius, also at 750 torr. Because we have a constant pressure, we will be using Charles' Law. Charles' Law is V1 over T1 is equal to V2 over T2. Whenever we calculate gases, we must be using Kelvin. So I'm going to separate my variables here. My V1 is 0.300 liters. My T1, because I have a digit past the decimal, the general rule of thumb is if you have a digit past the decimal, you use 273.15. If you do not, you can truncate that at 273. The reality is, in my classroom, I will do my best to have that rounding error accounted for in your answer. So the V2 is what I'm looking for, and then the T2, we take 30 and add it to 273.15, and you should get 303.15. So now we plug in the values where they belong. And now we can do this calculation. So the first thing I'm going to start with is 0.3 divided by 283, and I get a value that is 1.0. I'm going to give you too many digits because I'm just going to leave it in my calculator. And I'm going to leave off the unit now. And so that is equal to V2 over 303.15. Now the algebra is we multiply both sides by 303.15, and that is my V2. So V2 in this case is going to be a 0.321 liters. I had 3 significant figures in my measured quantities. I need to report 3 significant figures. Now I have also calculated it without the 0.15, and I still get 0.321. So let's run through another one of Charles' Law. If we have a sample with a volume that is 150.0 centimeters cubed at 0 degrees Celsius, when it's immersed in a liquid, its volume changes to 131.7 centimeters cubed. So what is the temperature? Well, here I'm going to assign these my 1s and I'm going to assign these my 2's. So volume 1 is going to be 150 centimeters cubed. Volume 2 is going to be 131.7 centimeters cubed. But what do I do with this volume? This isn't liters. Well, the reality is, as long as your volume units are the same, your pressure units are the same, and your temperatures are in Kelvin, you can still do the calculation. So I can leave these units as they are. Now my temperature 1 is going to be 0.00 degrees Celsius, which I need to add my 273.15 to. So temperature 1 is going to be 273.15 Kelvin. Temperature 2 then is what I don't know. So let's fill in the numbers we know. We need to keep the 1's with the 1's, so V1 with T1. And then V2 with T2. So I perform this arithmetic. 150 divided by 273.15, I get a 0.549, and I'm going to end up leaving that in my calculator. And that is equal to 131.7 over T2. Now the algebra here, you multiply both sides by T2. Now I divide both sides by 0.549. And I get a value that is 239.82. I'm giving you too many digits on purpose, 857 K. The part I left out, what is the temperature in degrees Celsius? That's why I gave you too many digits. So we need to take this, all of this business, and we will subtract 273.15. So the number that I get is a negative 33.3 degrees Celsius. We started with 3 significant digits in my initial temperature, so I'm going to end with 3 significant digits in my reported temperature. With Boyles Law, now Boyles Law, Boyles Law is P1 V1 equals P2 V2. And I gave the example of a piston. So if we have a closed container and it has a piston, and we have a couple of gas particles in there and they're doing their thing, and then we compress that piston in order to decrease the volume, what happens is we still have that same amount of gas, but now they're running into the sides even more frequently. So that increases the pressure. So if we have a gas at a pressure of 2.20 atmospheres and its volume is 18 liters, what is the pressure if we expand it to 25 liters? Well, our P1 is 2.20, V1 is 18. We need to find P2, and our V, not L, our V is 25. So we plug in the values where they belong. Make sure that your 1's stay together and your 2's stay together. Now when we perform this arithmetic, so 2.20 times 18, I get a 1.584, and divide it by 25, I get a 1.584 atmospheres, and that's P2. Look up here, I actually can only calculate to 2 significant digits, so I need to look next door, and I'm going to round that up, and I will report 1.6 atmospheres for this particular example. The initial volume of a gas that starts at a pressure, so our initial pressure of 785 torr, and the pressure is decreased, so P2 is 745 torr, and the ending volume, the final volume, is 0.55 liters. So we're looking for V1 in this case. Now I still plug in my numbers where they go. Remember, we're using P1 V1 equals P2 V2. We're still using Boyles Law here. So we have 785. I'm going to leave that as torr. V1 is what I'm looking for. P2 is 745 torr, and V2 is 0.55 liters. Now, when your pressure units are the same, you can leave them as they are. So if I go through this arithmetic stepwise for you, I have 745 times 0.55, I get 409.75. Then I need to divide both sides by 785 in order to get my variable by itself, and I get 0.52197, etc., and that's going to be liters. Now I only have two significant digits here. I can only report two significant digits here. I look next door, that's a 1, it's too small to round. So 0.52 liters is what I would report. Now we do have what's called the combined gas law, and it's something that you may see, but it's really just taking Charles and Boyles and squishing them together. And the combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. So I'm just going to run through one of these real quick. So if we have a sample at 1 atmosphere, and that sample occupies a volume of 1.7 liters when it's at a temperature of 298 K. What is the new pressure when the volume is expanded to 2.0 liters and the temperature rises to 310 K? See, this decimal right here makes this digit significant. So we plug in what we know and we solve for what we don't. It's the same pattern we were doing before. So I'm going to plug in my 1.0 atmospheres and my 1.7 liters, divide it by 298 K. That's going to be equal to P2, which I don't know yet, 2.0 liters, divided by 310 Kelvin. So when I perform this arithmetic, I get my 1 times 1.7, and I divide that by 298. I end up with 5.70 times 10 to the negative third. That's going to be equal to P2 times a number, that's 2, divided by 310, and I get 6.13 times 10 to the negative third. Now I divide both sides by that 6.13 times 10 to the negative third, and I'm leaving these numbers in my calculator to try to avoid some rounding error. So my new pressure is 0.88 atmospheres. So although we increased the temperature, we also increased the volume. That ended up decreasing our pressure. So now let's work with Avogadros Law. Now Avogadros Law is a relationship between volume and moles. In short, the more moles you have, the more volume you're going to have. So if you have 4.7 moles of a gas and it has a volume of 1.7 liters, what is the volume if we have 23 gas? So what is the volume? These are my ones, these are my twos. I'm going to plug in what I know and then run the arithmetic. So volume is on top, then my moles of gas, and that is equal to the volume I do not know divided by the moles I have. Now just have a look at this expression real quick. It looks like we're making equivalent fractions. You know how 1/2, if you multiply both the numerator and the denominator by 5, you end up with 5/10? That's what we're doing here. We're just solving for what that value is. So we run this arithmetic, 1.7 divided by 4.7, and I get 0.3617, and that's going to be equal to the volume I don't know, divided by 23.5. Multiply both sides by 23.5, and I get a volume of 8.5 liters. So when I multiply the number of moles of gas I have by 5, I'm also multiplying the volume by 5. Now the last of the gas laws the simple gas laws we're going to look at is called Dalton's Law of Partial Pressures. So this is Dalton. Dalton's the one who gave us the atomic theory. We also have this partial pressure. Now it seems rather intuitive that the pressure of a mixture of a gas is going to be comprised of the pressures of its parts. Specifically, what I want to look at is the pressure of the atmosphere. So the pressure of the atmosphere is going to be comprised of the gases in the atmosphere. So that's nitrogen, that's oxygen, there are primary players. And then we have what I'm just going to call other. So this other makes up about 0.01 of our atmosphere. So we have 1.0 atmosphere at sea level. And the other is going to be like carbon dioxide, argon, neon, methane. Sometimes if you live in a rural area, you might have more methane, helium, krypton, etc. All of our minor gases that actually has a partial pressure of 0.01 atmospheres. Now, the partial pressure of nitrogen in the atmosphere is usually about 0.78 atmospheres. So what is the partial pressure of oxygen in our atmosphere? Well, whenever you're using Dalton's Dalton's partial pressure equation, as long as your pressures are the same unit, you can just add and subtract at will. So here we have 1.0 is equal to 0.79 plus our variable. So I've added 0.78 and 0.01. So the partial pressure of oxygen, if I subtract 0.79 from both sides, our partial pressure of oxygen, and I should put another 0 there, is 0.21 atmospheres. So that's using Dalton's law of partial pressures. Next, we're going to use the ideal gas law.